working on an offshoot of the Organic Cropping Systems project that Brian Caldwell was talking about this morning in the grain section. And what we've been doing is trying to figure out what effects organic fertility sources have on weed growth, and in particular what nutrients are playing the most important roles. There we go. Okay, so the motivation of this project is that many people have observed that as you apply increasing amounts of fertilizer, the crop yield increases, and then it levels off at a certain point, and after that point, adding more fertilizer doesn't really get you any benefit. But certain weed species seem to keep getting bigger and bigger even after the point where you've added all the fertilizer that the crops can use. And this has been mostly studied in inorganic systems, but it is also relevant to organic systems, particularly with people like dairy and organic vegetable farmers who apply a lot of compost or manure, because these fertility sources don't have a sort of a set ratio of nitrogen to phosphorus to potassium to all the other nutrients. And that's not ideal for nitrogen in particular, because people often apply enough compost to supply their crops' nitrogen needs, and that tends to over-fertilize with phosphorus and potassium and several other nutrients. And so if the weeds are able to take advantage of this extra phosphorus or other nutrients, this could result in a decreased yield if you're not able to control the extra weed growth, or would at the very least result in increased weed control costs. So the questions that my experiment has been working on are trying to figure out what nutrients in compost at high rates the weeds are responding to when the crops have stopped responding to such high rates of compost. And also, can we continue to fertilize with compost at the amount necessary to supply the crop's nitrogen needs, or do we need to integrate some other nitrogen sources? And if so, how can we optimize the combination of the organic fertility options that farmers have? So the methods for this experiment were, we spent 2 summers on this, one at one field site in Aurora, New York, and then the next summer we moved to another field site in Ithaca, New York, so they're pretty close by, about an hour apart. The first field season, that's what this picture is, had a lime silt loam that was right next to the Organic Cropping Systems experiment, with medium phosphorus and medium-high potassium and a really high pH. And what we did was, it was in sod before we used this field site. And there were, it was mostly grass, but there were clumps of clover spread around. So what we did was we spread alfalfa hay in between the clover to try to make sure there was an equal amount of nitrogen across the field before we plowed. And in the second year, we moved to a site with a much lower pH, for reasons I'll talk about a little bit later, but still had low phosphorus and did have high potassium, which was good because by the second year we ruled out potassium as the culprit for the weed growth that we'd observed. So we wanted that to be supplied by the soil and not by our experimental treatments. But this year, since this field site had such low pH, we had to add some lime at the beginning of the season before we plowed in order to increase the pH to a level that the crops would grow, because it's a potato farm and we weren't growing potatoes. Yes, and this was also in sod before we did this experiment. Something I probably should have mentioned is that this year, the first year, we grew the crops in little boxes in the ground, so we could apply fertility treatments to small areas. And that worked out well for the fertility treatments, but it took a long time, so planting was delayed. So the second year, just this past summer, we planted in rows, which was a lot more time efficient, and spread the fertilizer in plots and then planted across the rows. So we used three crop species, field corn and lettuce, and then in the second year we added kale as a third species. So the field corn and the lettuce we grew the first year and the second year, and then in the second year we added the kale. And we had several weed species we were looking at also. The first 3 we did both years. Giant foxtail, Powell amaranth, which is our most common pigweed, and I'll be calling it pigweed for the rest of this talk. And also common lamb's quarters, and those we grew in both years. And then in the second year we added in velvet leaf, because these 3 species have very low to no association with mycorrhizal fungi, which often supply plants with phosphorus. And velvet leaf does associate with mycorrhizal fungi, so we wanted to have some difference in the phosphorus acquisition strategies among our weeds. So we used composted poultry manure as our fertility source, our representative fertility source. And it's important to note that when I call it compost, it's not, it's kind of an unusual compost. It's basically chicken manure dried for a while. It doesn't have any litter in it, so it's got low organic matter, but compost was the best word we could come up for it. And so what we did was we applied increasing rates of this compost, and then we tried to mimic the nitrogen or the phosphorus or the potassium in those amounts of compost, using either blood meal for nitrogen or bone char for phosphorus or potassium sulfate for potassium. So the methods were a little bit different the first year and the second year. In the first year, we had a range of compost rates to get a range of nitrogen and phosphorus and nitrogen rates from, we're very low, most people wouldn't apply this much, to really high. And then we mimicked those amounts of nitrogen and phosphorus and potassium with our other sources. So we had a low rate, and then we had multiples of that increasing with the compost. And then we mimicked it with the other sources. And if you're interested, we've got the pounds per acre of compost that we use to get those nutrient rates. And in the second year, by the second year, we ruled out potassium as a factor that was influencing the weeds very much. So we focused more on nitrogen and phosphorus. And so what we did the second year was we applied either the extension recommended level of nitrogen or phosphorus, and then increased compost on top of that. Or we applied the extension recommended level of nitrogen or phosphorus, and then increased nitrogen on top of that, or increased phosphorus on top of that. The problem with this method that we encountered was we were trying really hard to find a just phosphorus organic source to mimic the phosphorus in compost that would be available readily, and it turned out that our phosphorus source didn't supply phosphorus in the first year that we applied it in either of our 2 years. That's the control is the gray bar where we didn't apply any nutrients. The blue is the bone char that we applied to try to mimic the phosphorus in compost, and this is the compost, and this is the plant available phosphorus in the soil at the end of our experiment. So our phosphorus treatment didn't really work. But we do have some good data on nitrogen and potassium in compost, so I'll be talking about that for the rest of this talk. So results. Pigweed was our coolest plant, had the biggest differences among treatments. These are pictures from the first year when we were still growing things in boxes, but the results were very similar in the 2 years. In the control treatment, where we didn't apply any nutrients, it was just the soil that with the sod had been plowed under. The pigweed was very small, about this big if the picture's all grayed out. But in the highest rate of our compost treatment, pigweed was a lot bigger. And this is also interesting because one of the experiments that we sort of inspired this study was on a collaborator farmer's farm, Klaus Martin's, where they couldn't max out the growth of pigweed with rates of compost even to the point that was 3 times what maxed out the crop growth. And we haven't really managed to max out the pigweed growth either, so it just seems to get bigger and bigger and bigger the more compost you give to it. But what was really surprising to us was that our treatment where we added nitrogen and potassium to match what was in the compost, the pigweed was still just as small as it was where we didn't give it any fertilizer at all, despite this huge response to compost. So this suggests to us that this huge response to compost is not to do to either nitrogen or potassium alone or together, just with each other. And we've got the graph here from the second year of the experiment. All the graphs I'll be showing you are from this most recent year. On the left axis, we've got the dry above ground weight. And on the bottom, we've got the increasing rates of whichever fertility amendment is relevant to the line. The red solid line is the biomass, the growth with increasing amounts of nitrogen as blood meal. and the dashed gray line is the growth with increasing amounts of compost. And you can see the pigweed just keeps getting bigger and bigger and bigger with more compost and doesn't seem to do much of anything when you give it more nitrogen. The lamb's quarters is very similar to the pigweed. It just keeps getting bigger and bigger and bigger with high rates of compost and doesn't seem to be responding to the nitrogen. The wrong direction, sorry. The foxtail, the giant foxtail, had a relatively minimal response to either of them. There might be a little bit of a response to increasing amounts of compost, but it's not statistically significant, so I'm not going to emphasize that too much. Velvet leaf, though, the weed we added in the second year, the one that does associate with mycorrhizal fungi, interestingly, is the only one we've seen so far that responds to nitrogen the same way it responds to compost, where its growth increases as you give it more. So we think that's a really interesting result that we'd like to look into a little bit more. Corn, this is the field corn, didn't respond very much to anything. There was a small increase with increased compost, not really any response to increased nitrogen. And so this suggests to us that because we plowed under the sod at the beginning of the summer, there was a decent amount of nitrogen in the soil already for the crop, for the corn, so that most of the nutrients it needed were in the soil already. So that's especially interesting to us that with that level of nutrients in the soil for the corn to have a decent yield without additional nutrients. The weeds still were getting huge with increased amounts of compost. And I've tried to calculate, we've got this in grams here, so I tried to calculate the equivalent of silage tons per acre. This is definitely an overestimate because no one grows corn, just one row of corn. That's weird. But you can tell, I guess, what ballpark we're in. I think this is, about 17 bushels per acre. No, other way around, it's larger. Yeah, I had that written down and then I forgot, I'm sorry. Something like 1 point something bushels per acre, right? So there's 17 bushels in per.
Multiplied by 5.
I better not do math right in front of everybody. That's not the, I shouldn't do that. Yeah, and so kale, the crop that we added the second year, was kind of messy, largely because I think we had a lot of trouble with flea beetles. But it seems like it might have a small response to low levels of compost. But that's definitely not statistically significant because there's a lot of variability. The lettuce, though, does have a significant response to compost. As you increase the compost, the lettuce gets bigger. And this does jive with what our extension recommendations, what the extension recommendations are, that really high rates of compost are what a lot of growers apply and what sometimes people recommend too. But the important thing to remember is that lettuce is a really poor competitor with weeds. It only gets about this tall. So at these high rates of compost amendment, you would need to have really good weed control to maintain any yield benefit of applying that much compost. So if nitrogen and potassium don't explain the pigweed response to compost, what's going on? Probably not organic matter because there's no litter in this poultry manure compost. So that shouldn't be affecting the water holding capacity of the soil. It's probably not sulfur because the potassium sulfate that we added had sulfur in it and they didn't respond to that. We think phosphorus probably has something to do with it because our treatment for phosphorus didn't supply any available phosphorus, so we didn't really test whether the weeds are responding to phosphorus in this experiment. Also, we had a small greenhouse study that I didn't show you the data from, with several different phosphorus sources at different pH levels, trying to trying to get some phosphorus supplied. And we did see a sort of intermediate growth in pigweed between a control with nothing added and the compost, which was always very much bigger. So it seems like there might be an interaction with phosphorus and some other nutrient. But we really don't know that yet. The velvet leaf response, the velvet leaf was the only one that responded to nitrogen, and that's one that has associations with fungi in the soil that supply phosphorus. Suggests to us that phosphorus might have something to do with it, but also because it gets phosphorus from the fungi, then it might be more limited by nitrogen. So maybe weeds that don't get phosphorus from fungi might be more limited by phosphorus. But we really don't know yet. There are a couple of other nutrients that we think might be players. There's zinc and manganese. They're micronutrients, so people don't tend to think about them too much. Is that the timer? Okay. But there is a high level of zinc and manganese in the composted poultry manure, so that could be something that's worth exploring in future research.
That's 5 minutes.
5 minutes? Okay. I'm going a little fast. So what we're going to do next is that we're going to analyze the nutrients in our plant samples from all these different treatments. And that means I get to use this really cool machine that heats the plants up, and then the electrons get excited, and as they get less excited, they send out light, and you can figure out what elements are in them that way. And the goal with this will be to try to figure out which nutrients are limiting which plants under which conditions, and hopefully get a better idea of what in the compost the weeds are responding to that isn't causing increased crop growth. So back to our original questions, what nutrients in compost are weeds responding to? Can we continue to fertilize with compost at rates to supply crop nitrogen? And how can we optimize organic nutrient amendments? So in conclusion, it's definitely true that certain weeds respond to high rates of compost more than certain crops do, at least when there's a decent amount of organic matter in the soil, like there was when we plowed down a sod for these experiments. And pigweed, it seems in particular, is really responsive to high rates of compost. And I guess sort of the main conclusion is more is not always better when it comes to applying compost. Sometimes we like to think that it's organic, it's good for us, let's just put on as much as we've got, and it suggests that some is good, some is necessary to feed the crops, but if you keep adding more and more and more, you may be running into problems with your weeds. And we may need to reevaluate compost application for nitrogen needs. Maybe some other nitrogen sources like cover crops might be good to try and get some of the nitrogen need from a just nitrogen source, and then you could apply lower rates of compost and not oversupply whatever nutrient it is that the weeds are responding to. And except for velvet leaf, the weed response doesn't seem to be to nitrogen or potassium. So it doesn't seem to be the nitrogen or the potassium in the compost that the weeds are responding to. So that suggests future areas for research. We've ruled those out. We can look at other nutrients now. And lettuce yield does seem to benefit a bit from high rates of fertility, but weed management would be crucial in that situation because you'd seem to also get increased weed growth at those high rates of fertility. And hopefully with further research, that's kind of what everyone says with these talks, I guess, but hopefully someday we'll be able to figure out a little bit more about which nutrients are driving the high weed growth at the high compost rates, so we can try and optimize fertility amendments so you can feed the crops more than you're feeding the weeds. I was funded for this project. This is my master's thesis by the Towards Sustainability Foundation. They were kind enough to fund it 2 years in a row, and the Cornell Crop and Soil Science Department. And there was a lot of digging holes and thinning foxtail, and I'm incredibly grateful to all the wonderful people who helped with that.